Bayesian Logistic Regression. Let's see. Let's take an example application. Suppose you want to predict the eligibility to sanction a particular loan based on various parameters like the income level of the person, the demography, the age, and maybe a lot of other characteristics. You can treat this as a classification problem and use logistic regression to see what is the probability of a person being granted a loan. Now, that's great. But once we use a model to make this prediction, how confident are we about the prediction? Can we right away use it to reject a loan? Probably not. And how confident we are enables us to make the right interventions. So let's first recap logistic regression. So in logistic regression, we define probability of success, or y equals 1 equals sigmoid of W transpose X plus B, where y is 1 if a person is granted a loan in this case and 0 otherwise. And the goal is to find the best parameters W here, or the weights. And the standard way of doing this is to use gradient descent with maximum likelihood estimate, or there are a few other techniques to do this. Now, how do we know if our logistic regression model can handle uncertainty? So let's say we are given a new data point and we have to predict for this new customer whether to grant the loan or not using the model we already learned. In other words, using the parameters of the model we already learned, we compute P of y equals 1. Suppose we get something around 0.5. In this case, it's hard for us to say whether it's an approval or not, because the probability of y equals 1 is neither high nor low. So this is one way of saying, I trust my model parameters, but I'm not confident about the outcome for this data point, because my model is not able to tell me confidently for this data point. Now, scenario 2, what if I'm not confident about my model parameters themselves? Like, how confident am I about my model itself? For example, let's say we trained a model with just 10 data points and all of them are loan rejects. Given a new data point, very likely it will just reject the loan for this new customer, because all it has seen is rejects, and it will reject with a lot of confidence. So P of y equals 1 will be like really, really low. But that does not mean that we can actually trust this outcome, because the model might not have been trained with enough data and we are not confident about the model itself. But the problem is, in the normal scenario, there's no way for us to learn, or there's no way for us to know this. So Bayesian modeling is a way to help us know when we are not confident. So in the Bayesian approach, what we end up doing is, instead of learning these parameters W, we actually learn a distribution over these parameters. And as we do so, we can see from the variance of this distribution whether we are confident about the model itself or not. So if I want to express the same thing that I wrote earlier for logistic regression, in a Bayesian sense, I would say P of y equals 1 given W, because I now treat the parameters W themselves as random variables, is sigma of W transpose Xi plus B. So when we think of Bayesian models, it's customary to first think of a generative process. So whatever we know about logistic regression, and we have seen so far, let's write it in a generative process which defines how data is generated using this process. So the data here is nothing but outcomes, whether people got loan approvals or people got loan rejects, right? So that's the yi's. Let's say there are m features and n data points. So for each feature, for j is equal to 1 to m, I take the weight corresponding to that feature and I'm generating it from a prior. And then for each data point, for I equals 1 to n, I actually say yi is coming from a Bernoulli of sigmoid W transpose Xi plus B. And this is same as saying P of yi equals 1 is sigma of W transpose Xi plus B. It's just a generative way of writing this in terms of a Bernoulli distribution. Now, what is the task at hand if we say we want to learn the model, given we have defined the generative process and so on? To learn the model, we need to learn the parameters, or rather a distribution over the parameters, and this process is called inference. So W are the parameters are now random variables. They are coming from a prior distribution, and now we have probability of y equals 1 given W equal to, there's an equal to missing here, sigmoid of W transpose Xi plus B. This is what we have seen earlier. The inference process involves finding the distribution of the parameters W given the data. So P of W given Y is what we want to find out in the inference process, and that's P of Y given W into P of W, coming from Bayes rule. And this is proportionality, of course, it's not equal. Okay, so now, great, but how actually do we find this distribution, P of W given Y? We know it's proportional to this, but how do we go about it? Now, there are two standard ways that people have been doing this, and actually there are many ways of doing something called approximate inference, when we cannot find, a mathematically tractable way of just evaluating the distribution. And popular methods are variation inference, Gibbs sampling, and so on. But we can also use TensorFlow probability here, because this specific problem, a logistic regression, can actually be expressed as a simple neural network. So think of, a very simple neural network with just the input layer, which is taking in all the features, and there is only one output point. There are no hidden layers, and there's only one output node which has a sigmoid activation function, right? And it can use the cross entropy loss. So if we are doing binary classification, it will use the binary cross entropy loss. Now, what is nice here is that using TensorFlow probability, we can specify priors for these weights. Or we could rather say that we want to do Bayesian inference for these weights. And this is in fact called a Bayesian neural network. In fact, here is some code from TensorFlow probability website, which shows how to do Bayesian logistic regression. It's similar to the simple neural network that we just defined that you would normally do, like just a input layer and an output layer, except that we are actually specifying that this is a Bayesian layer here, where we want to put a prior over the weights and do inference over it, right? And the rest of it is pretty similar to how you would define a normal two-layered neural network without any hidden layers, right? And you're specifying the optimizer here and the loss here to be binary cross entropy for binary classification and so on. And I'm not going into too many details here because that might not be within the scope of this particular talk, but I will have a separate video for Bayesian neural networks. And here are some of the references. You can actually go to the TensorFlow probability website to get more details. To recapitulate, we looked at Bayesian logistic regression, which enables us to capture parameter uncertainty when we try to do binary classification with logistic regression. Thank you.